Okay, we're going to talk about synthetic division. This starts our section 2.2 in the book. This ought to really be called the hunt for zeros, or the beginning of that process. But I know most of you, and hopefully everybody that's viewing this video has some familiarity with synthetic division. If not, you're going to need that in order to understand what's going on in this. But I was using synthetic division for years before I really understood why it worked. I just thought it was pretty cool that it did work. I'm going to go through this synthetic process right here and hopefully give you some feel for why this works. So if we were synthetically dividing into this polynomial, I would have coefficients A, B, C, D, and E. And let's just say for the sake of it, I'm just synthetically dividing X into this value. We're going to take all the numbers out and do a little theory here. So we know we would bring the A down, multiply it by X, add B to that, multiply that result by X, and I'm going to distribute through the X, so I get AX squared plus BX. To that, we're supposed to multiply C, or excuse me, add C, I'm sorry. So we get AX squared plus BX plus C. We multiply that by X. I'm going to distribute through again. And I get AX to the third plus BX squared plus CX. Add to that D, and I get AX to the third plus BX squared plus CX plus D. Multiply through X, distributing that, and I am AX to the fourth plus BX to the third plus CX to the, I'm sorry, plus CX to, that I was blocking my own light, plus CX squared plus DX. And then when I add E to that, you note that we're right back to there. And that's the reason that works. And what's kind of interesting on this, if we pick a value X or 2 or 7, whatever, notice what happens with our A value here. A gets multiplied by X, and then A again gets multiplied by X. Each step, we're multiplying by another X. So ultimately, the A gets multiplied by X 1, 2, 3, 4 times. Likewise, the B gets multiplied by the X 3 times, as we can see over here. So kind of a neat process. And if you don't have a graphing calculator, or a calculator, it could be quite a time savings device for us as well. So anyway, that's why synthetic division does some of the things it does for us. Pretty neat. Okay, in this case, we're not using synthetic division. Synthetic division is not real practical when we don't have a lead coefficient of 1. Yes, we could factor a 2 out of that and synthetically divide 3 halves, but we have to account for that 2 later on. So we're just going to go ahead and use long division here. So I'm going to take 2x minus 3 into, and I notice I have an x to the third, x squared, a plain old x. I don't have any holes. We have to really be alert if we have any holes in here. 2x to the third minus 3x squared minus 50x plus 75. Okay, now I'm just going to go back and look at a simple little division problem here. If we were going to take 8 into, say, 49, we would say 8 goes into 49 6 times. 8 didn't go into 4, so I didn't put the 8 over top of the 4. 8 goes into 49 6 times. We get 48 and 1. And we know that when we were just starting out, we would say that's 6 remainder 1. But we also know we can write that as 6 and 1/8. Here's a point I want to make with this. We also could say then that 49 equals what I divided by times my quotient 6 plus just plain our remainder 1. So anyway, I always like to kind of relate something new to something old. So 2x minus 3 goes into 2x goes into 2x cubed 2x, or excuse me, x squared times. I'm going to put that over my x squared column. So I take 2x minus 3, 2x times x squared, and I get 2x cubed minus 3 times x squared, and I get minus 3x squared. But what did we do over here with the 48? I subtracted 48, so I need to subtract all of this. So I go through and I just change the signs. I'm going to make this one a minus, make this a plus. And we get 0, coincidentally, plus 0, and I bring down the minus 50x. And because I got an additional 0, 2x minus 3 doesn't really go into minus 50x, but it might go into minus 50x plus 75. So really kind of have a 0 right here. So 2x goes into negative 50, negative 25 times. That gives me negative 25 times 2x, negative 50x, which I needed. And coincidentally, minus 25 or negative 25 times minus 3 plus 75. But once again, what do I do each step? I subtract those values, so that makes this minus negative plus, plus negative, and I end up with 0. So our solution is x squared minus 25, which tells me a little bit more. That's the final book answer, but it really tells me that this guy is equal to 2x minus 3 times that, or 2x in this case minus 3, easily factorable, x plus 5, x minus 5, and we would say that is the linear factorization, because each of these is a line. And if we set it equal to 0, we would quickly see that our zeros are add 3, divide 2, subtract 5, add 5. So those are our 3 zeros of our polynomial. Now we can synthetically divide. And to synthetically divide, we're going to set this up with coefficients. Notice I do not have an x squared term here. That creates a hole. So I have 5x cubes, no x squareds, 6x's, and a constant of 8. X minus 2, synthetic division, or x plus 2, synthetic division really works based on what I refer to as the Mivoc's most interesting value of x here is negative 2. It's really based on like dividing in x minus k. So in this case, k is negative 2. I'm taking negative 2 into this guy. So we're to synthetically divide that guy. So I get, bring down the 5, multiply by negative 2, add them, multiply by negative 2, add them, multiply by negative 2, add them, negative 44. So what we found out is the solution to this would be, this was an x cubed, it becomes an x squared. So we get 5x squared minus 10x plus 26 with a remainder of 44, but that would be minus 44 by what I was dividing by, and I was dividing by x plus 2. So that is it. If you're a big fan of long division, you could just long divide that as well. Okay, write the function in the form. This is kind of a weird one. This goes back to my example. When I took 8 into 49, and I got 6, 48, we subtract those 1, remainder 1, I wrote that 49 could be written as equal to what we're dividing by, that was 8, times our quotient, 6 in this case, plus our remainder, 1. And that's what we're supposed to do with this guy. So write a function in the form of f of x. I'm going to divide this. Now when they have k as negative root 5, that's like saying we're looking to divide by x plus root 5. I've got to the third, to the second, to the first, no holes. So I'm going to set this up as 1, 2, -5, -4, and I'm synthetically dividing negative root 5, which seems like it might be messy, but actually turns out pretty nice. So I bring down the 1, multiply negative root 5. I add those together, 2 and negative root 5. I multiplied those by negative root 5. So negative root 5 times the negative or the minus root 5 gives me a positive 5. And negative root 5 times 2 minus negative or minus 2 root 5. When I add those together, I get a nice canceling here. And I end up with just minus 2 root 5. Multiply that by negative root 2 or root 5. That's positive 2 times root 5 times root 5, 5, positive 10. And I end up with a 6 as a remainder. Therefore, just like here, I said 49, do that in red. I said 49 was equal to what I divided by times the quotient plus the remainder. That's how I want to piece this back together. So f of x is equal to what I divided by, x plus root 5 in this case, times my quotient. Here's my quotient in x squareds and x's. It's a bit messy here. So this guy is x squared plus 2 minus root 5 times x plus, or minus in this case, 2 root 5, and then I have to add on the remainder at the end, plus 6. So there we have it. A little bit of a mess in there. Okay. Use the remainder theorem. The remainder theorem for the very same reason as that first slide we looked at, where I was dividing x, synthetically dividing x into a, b, c, d, e. For that very reason, whatever remainder we get is the result. In other words, if I go ahead and run 2 through g synthetically, the very last value I get is what g of 2 is. So notice we got some holes here. I don't have any x to the fifths. I don't have any x to the thirds. I don't have any plain old x's. Be careful with that. Synthetically, then, this is 2, 0, 3, 0, -1, 0, 3. Double check. 2, 0, 3, 0, -1, 0, 3. So I want to synthetically run 2 through that guy. We'll do this. And I get, bring down the 2, double it. 0 plus 4, 4 times 2, 8. 8 plus 3, 11, times 2, 22. 0 plus 22, 22, times 2, 44. -1 plus 44, 43, times 2, 86. 0 plus 86, 86, times 2, 172, plus 3, 175. So, in that case, g of 2 is 175. Let me clear a little space for myself here. And now let's run 3 through this guy. So I run 3 through, I still bring the 2 down. 2 times 3, 6. 0 and 6, 6. Times 3, 18. 3 and 18, 21. Times 3, 63. And 0, 63. Times 3, that's 189. And -1, 188. And I should have a calculator sitting here with me, but I don't. 3 times 188. That 188 is 12 less than 200. 3 times 12, 36. So 36 less than 600. 564. And 0, 564 times 3. Well, 3 times 500 is 1500. 3 times 64 is 192. So 1692 plus 3, 1695. I sure hope that's correct. I think it is. So just is that necessarily a quicker way of finding g of 3 than putting 3 in here? Not if you had a calculator, but let's consider just 3 to the 6th for a moment here. 3 to the 6th is 3, then 9, then 27, then 81, 243, 243 times 3. It gets pretty big. So in the calculator age, perhaps if I had a calculator, I think I'd just probably enter it into that guy. But prior to that, that was pretty slick, and there's still certainly lots of good uses for synthetic division. This might perhaps not be one of the greatest ones, but that's why we know if we come up with 0 here, we then would know that x minus 3 was a factor. Okay. All right. Here's what all this is leading to. We're trying to find zeros and verify the given factors of the function, find the remaining factors. Well, if x plus 2 is a factor of, let's call this f of x, that means that negative 2 is a 0, because it would be x plus 2 times something times something times something. That would make negative 2 be a 0. That means that negative 2 should synthetically divide this and work out evenly, or x plus 2 should long divide it, work out evenly. I'm going to do synthetic division. 8x to the fourths minus 14x to the thirds minus 71x squareds minus 10x's plus 24, no holes. And I'm interested in synthetically dividing through our MyVox negative 2. Most interesting value of x. So I get 8 times 2, negative 16, and negative 14, negative 30 times negative 2, 60. Negative 11 times negative 2, 22. Positive 12 times negative 2, negative 24, and we end up with 0. So, yep, sure enough, that guy is a factor. And then I'm just going to continue from there and synthetically divide through 4. See if x minus 4 is a factor. After I've factored out x plus 2, x minus 4 would still have to factor out. So I get 8 times 4, 32. 2 times 4, 8. Negative 3 times 4, negative 12. And sure enough, factors. So far my factors include x plus 2, I'm going to just write it right up here, times x minus 4, times what would remain here is 8x squared plus 2x minus 3. And now we're at a quadratic, and I could start just making guesses at what other values might synthetically divide this evenly. But once we're at a quadratic, we pretty well have it made. I'm looking for two numbers that multiply to be negative 12 and add up to be positive 2. Then we could factor this guy further. Well, positive 6 and negative 4 work, so I'm going to make the outside product be, I'm going to choose positive 6. To get a 6, I'm looking for a 1 and a 6, or a 2 and a 3 from these guys. But I see I can use a 2 from the 8, so that's 2x, along with a 3 from the 3, and that would be plus 3. Now we got it made. I'll go to green. First term times first term has to equal first term, so 2x times 4x. And last term times last term has to equal last term, so plus 3 times minus 1. And there is my complete factorization. I'll write it here. I have a factor of x plus 2, an x minus 4, a 2x minus 1, and a 4x plus 3 factor. or my zeros are subtract 2, add 4, add 1, but divide 2, subtract 3, got 2 commas, subtract 3, but divide 4. And there we have it. That's a lot of what we're going to be doing with this material. Use the rational zero test. Oh, here's a good one. Rational zero test. I remember it being p's over q's, q's over p's. I'm not sure, but I knew I needed to find my factors of my lead term, 4. Those are plus or minus 1, plus or minus 2, plus or minus 4. I needed my factors of my trail term, negative 2. Those are plus or minus 1, plus or minus 2. And I always couldn't remember, or I could never really remember for certain. Is it the factors of this over this, or is it the factors of this guy over that guy? But any factor of this, if I had this guy all factored out into 5 linear factors, if that could happen, any factor of that, this times this, just my coefficients, times this, times this, times this, would have to equal 4, which means any one of those, the very first term has to be a factor of 4. And then times an x. The next term, this guy, times this, times this, times this, times this, has to end up equaling negative 2. So those have to be a factor of 2 or negative 2. I'm just going to call it a factor of 2 because they're the same factors. So I could go minus, I could go plus here. Again, plus or minus for all these factors. So every one of my factors meets that pattern. If I set that equal to 0 and solve, then I see I would get x equals subtract the factors of 2 over divide the factors of 4, although the minus is kind of irrelevant here because they're plus or minuses anyway. So it is the factors of 2 on top of the factors of 4. And that helped me. Once I knew that, I had it made. So I need my factors of 2 on top of my factors of 4. So I need 1s on 1s, that's plus or minus 1. I need 1s on 2s, that's plus or minus 1/2. I need 1s on 4s, plus or minus 1/4. I need 2s on 1s, plus or minus 2. I need 2s on 2s, but that's 1. I need 2s on 4s, but that's 1/2. That is all of the possible rational zeros. And now we would be charged with trying each of those. I'd have to try 1, try negative 1, try 1/2, try negative 1/2, try 1/4, try negative 1/4, try 2, try negative 2. Maybe none of those are zeros. And you may be saying, well, wait a minute. I know a 5th degree function has n model behavior like this and this, so it has to have at least a 0 somewhere as it wiggles. Well, it might just have a real 0 that's not rational. So there was never a guarantee. And back in the day, we had to exhaust all of these and try to find all of our rational zeros by synthetically dividing. And trust me, 4 and 2 are pretty manageable. So what a beautiful thing that our graphing calculators do for us here. I didn't have that luxury. I'm not bitter about that. I'm a little bit bitter about that. But we certainly don't have to do that now. But it doesn't mean that I might not keep you responsible for knowing where those guys came from. I just can't quite let it go yet. So that's our rational zero test. I have not found all the rational zeros. Those are just the possibilities. Okay, but I will leave the rest for the viewer. Okay, so as I was saying, to find all real zeros, what we had to do in the past was either hope we could factor, and that looks like no bargain on number 58 here, or we had to do this. I need my factors. What I've learned is that if I could factor this into linear factors, it would be a factor of 4 times x plus or minus a factor of 90. If I set that equal to 0, I would get x equals factors of 90 over factors of 4. So I'm interested in the factors of 90. Remember what I said on the last one, that that was a pretty generous, it wasn't a big sampling problem. There wasn't that many, I think there were only 8 options. How about this? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 9, plus or minus 10, plus or minus 6 times 15 works, plus or minus 18 times 5 works, plus or minus 30 times 3 works, plus or minus 45 times 2 works, plus or minus 90 times 1 works. Whew, that's just the 90s. Now I've got to go over the 4s. Plus or minus 1, plus or minus 2, plus or minus 8. Now, certainly some of these will be the same as others, but let's think about that. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 over 1, 2, 3. That's 36 possibilities plus or minus to check, and some of those will be repeats. Holy smokes. Yes, I am a little bit bitter. That's the kind of thing we used to have to do. What we can do now is we can go to our calculator and grab the rational zeros. We can find zeros that are rational and work. So that I'm going to leave to you, but you would go on your calculator, you would sketch a graph, you would use second calc 0, and then if you had a curve, let's say this curve looks something like that. I'm not saying it does, but I know it is a positive 4th degree. Then once you hit second calc 0, it's going to ask for a left bound. You would just float to the left until you were, say, here. Stamp it, then it'll ask for a right bound, float to the right, stamp it, stamp again, guess. It'll give you the location of that 0. If that is a rational number, in other words, if it's something like negative 2.6 and stops, then that's worth synthetically dividing. If it appears to be an irrational number, the decimal appears not to be repeating or doesn't stop, then we'd go and we'd repeat that process and hopefully find a nice rational 0 along the way. No guarantee you're going to get those, but certainly a wonderful option versus all of your factors of 90 on all of your factors of 4. So at that point, I'll leave that to the viewer to check on calculators, start the synthetic process, and good luck with this. It really is the search for zeros. That becomes a pretty important concept as we move forward.